Hello everybody, welcome back. Today we're going to discuss something called the interference of waves. And in particular, we're going to talk about sound waves, but these principles actually would apply to any kind of wave. The word interference, of course, means when two things sort of interact with each other. You might say that if you were trying to do your homework and your little brother was making a lot of noise, they would be interfering with you. So it's two things that are kind of working with each other or against each other. It's like an interaction. What we mean by interference with waves is when two or more different vibrations, or in fact even the same vibration, are working on the same medium at the same time. Remember that if we have a string, we vibrate the string, we push it up and then back down again, and we create this wave pattern in the string, this vibration which would travel down the wave. And if we kept going, we would produce a series of waves, a little train of waves that travel down the string. But what would happen if, say at the same time, that you wiggled your string and created your wave? What I'll do is I'll just do a half a one for now. Let's say you made this little bump that began to travel down the string, but at the same time, your friend on the other end made another bump. Let's make this bump like this, which was traveling this way. Well, eventually, those two bumps are going to meet in the middle. And when they do, they will interfere with each other. You see, each little bump or each wave crest that we've created is trying to move the string a certain way. So what would happen when they meet? Well, logically, when they meet, then they would add up their motion. Right? If you were trying to push something and your friend is also pushing that object, then you both push together, and your pushing adds up. So when we get to the middle, what would happen is we would add the two bumps and we would create one big bump, a larger bump. And if I were to say that this is the amplitude A, or amplitude 1, and this was amplitude 2, they don't have to be the same, of course, they could be any size wave, then the amplitude of the new wave would be amplitude 1 plus amplitude 2. In the one that I've drawn, the two waves are very close to the same amplitude, so when they meet, you get one that's about double the original. But it doesn't have to be double, it could just be the sum of the two waves. Now that's what happens when you have two bumps that meet. But you could also have a bump that you make, I'll do this one in red, but your friend wiggles the other way and makes a bump this way, like a crest and a trough meeting. Well, in the middle, what would happen there when they meet is it would still be the amplitude of wave number 1 and the amplitude of wave number 2. However, amplitude 2 is a negative amplitude, right? It's downwards. And so when you add them, A1 plus A2, because A2 is a negative number, that's going, when you add a negative number, that's like subtracting. And so you get a subtraction because they're in opposite directions. And when they meet in the middle, if they're exactly the same wave, they'll subtract from each other and produce a zero. I can't draw zero very well. I'll put a red section where the two waves are meeting. But you can see what would happen. The string would be pulled upwards a certain amount and downwards the same amount, and the result would be that the string wouldn't move at all in that particular spot. And so you would see as the two waves came together in the middle, they would suddenly disappear, and then they would emerge again as they pass through each other. That's the other thing about waves, is they don't collide and bounce. They pass right through each other. And so after the collision, you would see this zero, but then afterwards, you would see, here's the spot where they met. You would see this, with this one continuing on through and this one continuing that way. And so the interesting thing is that vibrations can add up to zero and can actually produce no vibration. It's kind of odd. The two things two very violent or vigorous vibrations could actually cancel each other out and produce nothing. And that's an important part of wave interference. So the simple way to describe wave interference is that when two waves interfere, the waves are added just like we would add any two things. And if you think about waves on a graph, so if I were to draw two waves, let's say I were to draw a green wave here, and then I were to draw another wave that was a little bit different, maybe in purple, something like this, then the way we would find out how an object would vibrate if both of these waves were passing through it would be to take the value at any point, say the y value, let's go here, this y value of the green graph and of the purple graph, and we would add them together and we would get this number. Or we could take the value here and here, this value, and add them together. And so basically you just go along the graph, and whatever the y value on this axis here is for the purple one, you also find in the same spot the one for the green one, and you add them together. And you can produce a new wave that will be quite complicated. What can happen when you start adding 1, 2, 3, 4, 5 waves together is the resulting wave can start to look something like this and get all sort of wiggly. It looks more like an echocardiogram when you listen to your heartbeat. Waves can become very complex. In fact, if you were to look at the wave of my voice, it would have so many wiggles and bumps in it that it would probably look something more like this, because it's a very complicated vibration. It's not a simple vibration. And so these patterns that we see are the results of many different vibrations acting at the same time, adding up with each other and producing bumps and hills and valleys that are quite irregular. Okay, let's look at a couple examples that are actually quite unique. Well, not necessarily unique, but interesting. Let's let's do it in graph form, and let's just kind of talk about how we graph waves. I'm going to try to do this freehand. It's kind of difficult, but if I take this red wave and I draw it like this, okay? Now, unfortunately, I think my wave got a little bit bigger each time, the amplitude, so I'm going to try that again, because it's kind of important that it look pretty accurate for this to work. So it was okay up to about here, I think. And I went a little too high. So let's take this wave. Okay. You'll just have to bear with me with the inaccuracy of the drawing. Let's take the very same wave. One way to distinguish between two types of waves is to consider their amplitudes that are different. You could make different frequencies, as I did up here. Here I had a purple wave that has a higher frequency than the green wave, and it also has a higher amplitude. But it's also interesting to take a wave and then use the exact same wave, but simply move it over. And you do this in real life by starting one vibration a little bit later than another. So if I started this vibration, remember the x-axis is time. If I start this vibration here, then this wave will be vibrating the same way if I do the exact same vibration, except that it'll be a little bit later in time, and so it'll be like delayed a little bit. And we'll get that wave pattern that looks like that. So if I make two waves that are the same, except I delay one, I get two waves. What we say is that these waves are out of phase. Out of phase. If you know anything about graphing sine and cosine waves in math, then you know that we often use angles on the x-axis. And we say that the phase angle is the difference. It would be how far apart the two waves are, this little piece right here. And we usually call that theta, or the phase angle. Okay? We don't really need to worry too much about that just yet, because we're just looking kind of superficially at waves, so I'll just point that out, because you're probably learning it in your trigonometry. But the word out of phase means that the two things are vibrating differently. It's hard to show that on the board, but I can kind of show you that. And I'm going to try to make a video of some demos that will go along with this lesson at some point. But I want you just to imagine for a minute that, you know, this is your hand. And it looks like one of the Simpsons' hands because it only has 3 fingers. Now let's say you wanted to wave your hand back and forth, like this. If you wave the other hand back and forth at exactly the same time, so that both hands go to the right and both hands go to the left, back and forth, they would be in phase with each other, both vibrating the same way. But what you could do is vibrate them sort of the same frequency, wave with the same speed. But what if you started by moving one hand this way and the other hand this way? Then the hands would kind of come close together in the middle and then far apart, close together, far apart. And they would still be vibrating the same way, but they're out of phase because they are not vibrating together. They're not both going left at the same time or both going right at the same time. The other thing you could do, that was what we would call completely out of phase, but you could also then just start moving this hand first so that it begins to go to the right. But then wait a few seconds before the other hand moves, so that the hand that I have on the right-hand side here would always be kind of lagging behind the other. And it wouldn't be sort of moving with it. It would be moving the same way, but would be kind of lagging behind because you waited a little bit longer to move it. And those waves would be out of phase. Okay? So out of phase simply means they're not matched up. They're not moving in the same direction at the same time. And so we can easily produce two waves that are out of phase like this. Let's see what happens if we try to add them together. Now what we'll do is, since we don't have numbers, we're just going to use some general techniques to get an idea or a picture of the wave. Let's look at all the places where one of the waves happens to be 0, because that's easy to add, isn't it? So let's look here, and here, and here. Okay. Now I just realized that my picture is a little bit out of whack, so it's going to be a little bit of a challenge, but that's okay. We'll get the idea. Here, here, all these spots, one of the waves is on the axis, so that means its value is 0. So let's go up here, right about there, let's say. And let's add the blue wave with the red wave. Well, red plus blue, red plus 0 is just red. So this green dot that I'm drawing here, this large green dot, represents the red plus the blue at this particular point. And this other one, I'm going to have to kind of bend this one a bit. It should have lined up more like that, and I kind of made a mistake there. In fact, they're all looking like they're a little bit out of whack for some reason. Maybe I should redraw that, because otherwise this is going to look pretty crazy. I'll have to redraw it a little more carefully. It's easier to have it drawn better than to try to make the bad drawing look right. So once again, I'll try and draw this red wave. The trick is I have to draw the second wave exactly the same as the red wave, except it has to be a little bit past it, which is why it becomes so difficult. So we'll give it a whirl. Come down here like this. Something like that. I'm hoping this will work. Okay. think this is going to work, with the exception of this little part at the beginning. Whoops, that's kind of a big tracer. All right, what I need to do here is just fix the blue one a bit. Should be something more like that. Okay, let's look at the green dots. Again, here at this point right here, okay, I have a spot. Now you'll notice that the red one is a little bit too high there, but this blue graph is at 0 and the red graph is here. So the value of 0 plus red is simply red. And over here I have red plus 0, which would put me here. The red is 0. 0 plus blue means I would just be blue. And then over here I have blue, 0 plus red, which is red, just the red number. Let's say the red number was -3. -3 plus 0. This is also a 0, so if I add it to blue, it'll just be whatever the blue is. And if I go along all the way wherever there's a 0, I can make these big spots, 0, 0, and I can get some places where I know, maybe I'll change those into purple so that they distinguish themselves from those green dots I drew. Because these are actual dots on the new wave. Now the other thing you can do is you can look at where the two graphs are exactly the same. For instance, right here, they both have the same value. If you add two numbers of the same value, then guess what happens? You get double the original value. So if I just look at how high that is, and I go about the same height, that would represent the sum of those two at that spot. Here they are also the same. And so if I double that, say about there, here, double it, here, kind of double it. I had to stretch that one kind of looks a little off. All these little triangular little shapes right here should all be the same on a symmetrically well-drawn graph. And here's one more. But that's enough for you to get a general picture or idea of how this graph or how this new wave is going to look. I can just draw it over top like this, kind of going through my dots. And you can see what happens. I get two waves that interfere with each other and produce a third wave that has a bigger amplitude. You see the amplitude of the purple wave being larger. When two waves interfere in such a way to produce a larger amplitude wave, we call this constructive interference. Constructive because it's making a bigger vibration. Constructive interference. If you got two waves to overlap as much as possible, you could get two waves that are, if the waves are in phase, which means they're exactly lined up with each other, so that would mean a red wave and a blue wave that was not delayed but right on top of it, those two waves would add up to the biggest possible wave, because here you'd be adding crest upon crest, trough upon trough, and you would get a wave that was much bigger, like that. It would be twice the size of the blue and red wave. That means they're in phase. And if they are in phase, then we would say that's complete constructive interference. It's the most constructive you can get. But it's possible, if I do this very quickly, to get a kind of interference that produces a smaller wave. So let's see what happens. Red. I can already tell that I drew that fairly badly because I was going too quickly, so I'm going to start again. I try to go fast, but speed kills, right? So let's go slow. Let's try to make this as even as we can. Not bad. And then if we take a blue one, but this time I'm going to start way, whoops. I'm going to start my blue wave way over here so that it goes like this. Just kind of trying to make this work out pretty closely. Okay. Now, if we do our little magic trick where we look at the zeros, right here, 0 plus red, 0. Okay, in fact, probably a little bit less than that. Well, in fact, why don't we just jump ahead to where the waves are equal, save us getting this all cluttered. Look here. If I double this distance, when I add those waves, it's only going to be that high. If I double this distance, it's only going to be that high. If I double this up, because I'm adding the waves together, you see, you're only going to get that high. And if you do the zeros, you'll get little points that are very close to that. And you'll get a wave that kind of only goes as high as this green one. So if this red and blue wave were to overlap each other, if they were to occur in the same medium, the result would be the green wave, which is a lower amplitude wave. So this is what we call destructive interference. Destructive interference occurs when waves are far enough apart, or when they are out of phase enough that when they overlap they produce a smaller wave or a smaller amplitude than what they each were originally. Now remember, with sound, this is kind of interesting. With sound, amplitude corresponds to how loud the sound is. Remember the intensity of the sound. So what's weird about this is you can add two sounds together and make a louder sound, like we did in this example. The purple wave has a bigger amplitude. So when you add red plus blue, you get purple, bigger amplitude, louder sound. But what is weird and hard for us to understand is that you can add two loud sounds, red plus blue, and get a quieter sound. It seems odd that two loud noises could actually work out to be quiet noises, but it can happen. The reason we don't notice it very often is because the conditions under which this happens have to be very, very, very carefully controlled and very specific. And normally in our everyday lives, there's so much sound everywhere around us that we don't get to notice this. But if you were to set up an experiment in a carefully controlled room where there were no other outside sounds, you could actually make this happen. You could make two loud sounds become a quieter sound by having the sounds out of phase with each other. But we'll talk more about that a little bit later. What we really want to do is we want to look at different ways that waves can interact with each other. So we have constructive interference and destructive interference. Those are critical, so memorize those ideas. Constructive is when waves interfere with each other to produce a larger amplitude wave, and destructive is when they interfere and produce a smaller amplitude wave. And by interfere, we simply mean add up. It's possible for a wave to interfere with itself, as you saw in one of the other videos and demos that we did. If you make waves, here's a wave in a string. When we did this with the slinky spring, the wave went all the way down to the end. And when it got to the end, it did something kind of interesting. I think I had the end of this that was tied up to the leg of a desk so that it wouldn't wiggle around or move too much. And what happened was that when the wave got here, it bounced backwards and it started to come back towards me. And we call that reflection. Waves reflect. And we like to think that the wave reflects off the desk leg, but not really. What the wave does is it reflects because it's reached the end of the medium in which it's vibrating. That's really what happens. And what's really cool is even if you didn't have a desk, if I just wiggled the wave and the end of the string was just free to swing whichever way it wanted to, the wave would still bounce back when it got to the end of the string. This is harder to demonstrate, but it does actually happen. So the reflection can occur whether or not you tie the end down, hold on to it with your hand, or if it's just free, kind of hanging there. We call this a fixed end, because fixed means it's held tight by something and isn't able to move. And we call this a free end. Or sometimes we use the word open end. And sometimes we use the word closed to describe this. So these words you should get to know. open or free end is the end of a medium that's vibrating freely and isn't held still, whereas a fixed or closed end is the end of a medium that is vibrating and is held still and not able to actually move. What's interesting is when you reflect off of the fixed end, when the wave bounces back, it bounces back upside down. It's what we call a phase inversion. It flips. So the crest becomes a trough and the trough becomes a crest. You see how this wave is coming back this way. In the first wave, I had it going this way so that the trough was leading the way. When it bounces back, that trough becomes a crest and the crest became a trough, so now the crest is leading the way. But when you bounce off of a free end, you do not have any inversion. And so when you bounce off of this end, the wave would stay in the same form. The trough would still be leading. So no phase inversion on a free end. So you see there's lots of little things you have to kind of get into your mind here to be able to understand where we're headed next. In our next video, we're going to talk about a very specific kind of interference that produces a very cool pattern of waves, and it's critical for understanding how sounds in things like musical instruments work. And that's our next little step. So for today, I just want you to understand what the concept of interference means. It means waves that add together. Because if you vibrate something and you have several different vibrations going through it, obviously they would all add up. But remember that when we add vibrations, that could mean that sometimes you're adding an up with a down or a crest with a trough, and you can get results that are less than what the vibrations were in the first place. So you can have constructive interference, where two waves are interfering together to produce a larger wave, or you can have destructive interference, where when you add them up, they actually do produce a smaller amplitude wave. We also have this idea of waves reflecting off of the end of the medium, when think about a string or a spring. And if the end is held tightly or fixed or closed, then when the wave reflects, it will reverse itself upside down. It will have a phase inversion. And when the end is free to wiggle, it will also reflect, but it will not have a phase inversion. So very, very important concepts. Just to summarize, what we sometimes do is we talk about complete destructive interference when two waves are lined up crest on crest, trough on trough, like this, the red and the black wave. That's what we call complete constructive interference. And then we can also talk about complete destructive interference, and that is when the waves are lined up trough on crest, trough on crest. These two waves would cancel each other out. The red wave is trying to push down, and the black wave is trying to push up. This would produce a zero wave, whereas this one would produce a double wave. Okay, so in the first case, we would have complete constructive interference, and we would produce a wave that was double in amplitude. So these two conditions occur when the waves are either completely lined up, right, in phase, and when they're completely out of phase, crest on trough. In mathematics, we say that they're 180 degrees out of phase. That's kind of important. Remember, 360 is the full circle. So halfway out. If you went 360, the wave would then fit nicely on top of itself again. But if you move it over, what we're basically saying is, watch how I draw this just to get the idea. The black wave would start here, and the red wave would have to start here and be exactly 180 degrees out of phase. And it would start like this. So the point where you're moving upwards on each wave is not lined up, but is separated by 180 degrees on the graph. If you went another 180 to make it 360, look what would happen. Right? If you started the wave here, it would start with the other one and they would line up again. So we use all that terminology: in phase, out of phase, 180 degrees, you could have any degree of out of phase, but this is the complete one. The one where you end up with actually zero, instead of just a wave that's a little bit less, like this green one we drew up here. You'll actually get a flat wave. A wave that just is flat, no vibration whatsoever. And again, that happens, but it's difficult to observe because of all the interference of all the sound around us. So in the next video, we're going to talk about something called the standing wave, after you get your head around all this kind of, these ideas about wave interference.